Hello everyone. I welcome you to the live section of this course, Introduction to Laser. I'm Geeta Anjali Jaina. I'm a PMRF scholar from IIT Delhi, and I'm a teaching assistant for this course. As I said before, in each live section, we will discuss the concept that has been taught during the this week, as well as we will solve the problems that is related to this concept, and I will clarify the doubts you must be having during for the assignment or any doubts regarding the concept. So we'll go through each assignment as well as each concept and some additional problems. So before starting the section, let me ask whether you have any doubts in the in the assignment 5. The solutions, this solution has been released in the NPTEL site, so you must be knowing the solution to his problem. So if you have any query regarding the solution of any question, so feel free to ask me now. I will first try to solve the doubts. Then we'll start this section. As well as
Uh,
one thing I wanted, yes,
Gitanjali,
yes, Nitish,
uh,
yeah.
uh, the in the up to four unit is uploaded. Fifth and the sixth week slide is not uploaded, ma'am.
Acha, Wix's slide is not uploaded.
Fifth and sixth,
Okay, okay,
and
okay.
also
Then, huh,
also solution of the assignment four is not uploaded.
okay, okay. Assignment 4 and week 6, right. Okay.
And
So
also
let
the
me tell the team to upload that. Week 6 slide I can upload in my site, my Google Drive link. And for the solution, I have to tell them. So week 4 solution, right?
uh, fourth and fifth, ma'am.
Okay. What?
And one doubt with the question
Eh,
number eight,
Question number 8
uh, assignment five.
and 5. So, okay. Please give me some time. Let me go through the question. And one thing I wanted to tell was, I think one student asked about the, I think, pattern of the exam. The pattern is like uh, it will be of, it's like MCQ type. There is no subjective, there no need to derive any formula or any lengthy process. Like one is MCQ type. So some of maybe direct recall type question, like if you know the concept, then you can directly know the answer. And some questions they are like a numerical type. So some parameters will be given, and you will be asked to find out what is the value of this and that depending on this parameter. So it will be mostly of MCQ type and numerical type. And each question they have equal marks, like 2 marks each. So I think you will be given 3 hours to solve this problem. So no need to worry about whether there will be subject or not. The pattern will be similar to what you see in the assignment. So it will be similar. So you just have to go through the concept, slides, and whatever sir has taught in the course and solve the assignment properly. So if you do that, then you can easily pass the exam. Okay. So regarding the doubt, question number 3. Okay. So I got the question. So the question is, in a particular symmetric plane mirror resonator with one longitudinal mode, the net intensity buildup after a large number of round trips is 9 E0 square, where E0 is the initial amplitude of the electric field. Assuming that there is no other cavity loss except the finite reflectivity of the mirror, the reflectivity R of each mirror is. Okay. So intensity is given and you need to find out what is the reflectivity. So for that, and these are symmetric plane mirror resonators, so they must have equal value of R1 and R2. So there is a relation, I think, I equal to I naught. Mm, net intensity value. Mm, yeah. So if you see this equation, this one, I equal to I naught divided by 1 minus R square divided by 1 plus 4R 1 minus R square sin square pi by 2. Here pi is not given. So if you take the maximum value of I, so what will be the maximum value? Okay, let me solve here only. So if you take the maximum value of I, it will be I naught divided by 1 minus R square. And I is already given. It's 9 V0 square. The I naught is nothing but V0 square. We put it 9 equal to 1 by 1 minus R square. 1 minus 1 by R is 3. So 1 minus R is 1 by 3. R is 1 minus 1 by 3, which is 2 by 3. And it is asking about reflectivity. So reflectivity is R square. So 2 by 3 square, it is 4 by 9. It will be 44, around 44.45%. Its answer is B. So, is this clear?
Yeah.
Oh,
So we have relation between the reflectivity and the reflection quotient R equal to R square.
yes, R equal to R square. And it is given symmetric planar mirror resonator. That means R of each mirror is same. So that's why we took R square. If they are different, then you have to take R1 into R2. So if they are different, the R will be R1 to R2. It's clear, right?
Okay.
Hmm. Anyone have any other doubt for the assignment other than this question? Okay. Okay, if you don't have any doubt, then let us start the section. So in the last class, we were discussing about what is the resonant frequency, what are standing modes in a plane mirror resonator, and what is the free spectral range, uh, how it is dependent on the length of the resonator and phasor diagram. So, so we have seen the cavity resonance. It's a symmetric intensity profile. So if you want to find out what is and the relation of the intensity, it is given as I divided by I max is 1 by 1 plus 2a by pi square sin square pi into mu by mu. So you don't have to remember all these formulas. It's like you just have to remember what is the relation, how this simple relation, how reflectivity depends on intensity, how intensity depends on the fineness. So only the approximation and the simple equation you just have to remember. You don't have to remember all this big equation. So it's like it won't be, if it is required, then it will be given in the question paper. So now, if you want to find out what is the line width of this cavity resonance, then what you have to do? So at line width, that is the full width at half maximum, the intensity will be half of the maximum intensity. So that means if you see the second term, so this is 1 plus there is a second term which is non-zero. So for I to be half of the maximum value, this term will be 1. So that means 2f by pi square sin square pi nu by nu f equal to 1. So if you take out the square, it will be plus or minus 1. Okay. And so here you can see you will get two values of frequency. One is before the resonance frequency and another one is after the resonance frequency. So for minus 1, you have nu 1 as nu minus nu f by pi sin inverse pi by 2. And for plus 1, it is nu 2. It is given by nu f by pi sin inverse pi by 2f. F is the fineness of the cavity and nu f is the free spectral length. That is the separation between the resonance, cavity resonance frequency. And for line width, it is nothing but the difference between this frequency nu2 minus nu. Okay. So if you take the difference, it will be 2 nu f by pi sin inverse pi by 2f. And for larger values of f, that is for when the cavity has more values of fineness, that is greater than equal to 10, then you can approximate the sine function as a sin inverse pi by 2f as pi by 2f. So for large value of angle, we approximate sin x as x and cos x as 1. So this is the approximation we made whenever the x value is small. So for sine term, it will be that solution will be pi by 2f. So nu f is, the line width will be nu f by f. So you can see the resonance, that is the line width, depends on the fineness as well as the free spectral range. So if you change the length of the cavity resonance, then the nu f will change. That is the separation between the cavity resonance, it will change. And according to that, whenever you change the cavity length, then the peak, that is the resonance line width, it will also change. So it's not like it is independent of the length of the cavity. So all these parameter depends on the cavity length. So now we'll talk about resonator loss and cavity lifetime. So these are some equation that we have gone through. That is the relation between I and I max, and the full width half maximum of the cavity resonance is delta nu is nu f by f. So this formula you have to recall because this will be required. And the free spectral range nu f is C by 2nl 2nl. So this formula you can easily calculate if you know the standing wave equation. So this formula you don't have to remember it. And the fineness f, it is given by pi root r divided by 1 minus r. So here you can see as you have seen delta nu, that is the line width of each cavity resonance. It is inversely proportional to the fineness of the cavity. And the cavity, the resonator loss in a cavity, these are defined by different parameters. This parameter is like pi r, which is the net resonator loss coefficient, and r, which is the round trip loss, which is related to the round trip loss. And this is the cavity lifetime. That is the energy. It is related to up to what time the energy is being confined or being oscillating inside the cavity. And the fourth parameter is the fineness. It is related to how sharp the peak is. So as you have seen, if you decrease the fineness, then the peak will become broader and broader. And other parameter is also used to define the resonator loss, which is quality parameter. So all these parameters are related. If you know once, then you can find out what is the parameter of what is the value of other parameter. So these are the equation, these are the relation that we will see in the next slide. So pi r, which is the resonator loss coefficient, fineness. This is also resonator loss coefficient, the relation between the cavity lifetime and resonator loss coefficient. And this is the approximation we made whenever r square lies between 0.9 to 0.9. And this is the quality factor and delta nu relation. We'll go through this. So, resonator loss, so it defines what is the losses per unit length whenever light is oscillating inside the resonator cavity. So the losses, it can be of many types. One is the because of the finite reflectivity of the mirror. That is, it's not total. It's not like a perfect mirror. So some part of the energy is getting transmitted to the other side. So that's why, because of the finite reflectivity, we'll see a loss due to the finite reflectivity. And another one is the propagation loss. Whenever the light is propagating inside the medium, so it will experience a loss due to the propagation loss. And this propagation loss, it may be due to the diffraction loss, due to the spreading out of the beam while it is propagating through the medium, or it can be of scattering loss. And alpha C, it is the propagation. So for propagation loss, we denote a term which is alpha C, which is the propagation loss coefficient. So now if you look at this diagram, the right diagram. So it is consist of two plane mirrors M1 and M2, and which is reflectivity, reflection coefficient R1, and I think this is reflectivity. Uh, okay, so which is reflectivity R1 and R2. So now when the light, when it is propagating through this medium, let's say the energy is omega zero at the first, and and it is starting from the mirror M1. So if you see, the light will propagate from here. So there will be propagation loss whenever it is propagating inside the resonator. Now it will get reflected at the mirror 2. So we'll see a reflection loss because of the mirror M2, which is R2. And after getting here, it will suffer propagation loss and a reflection loss here. So we'll see there will be two reflection loss and two propagation loss whenever light is after one round trip. The light will suffer a propagation loss, which is omega 0 e to power minus alpha Cl. There will be a reflection loss R2, and again propagation loss, which is denoted by e to power minus alpha Cl, and there is a reflection loss because of the finite reflectivity of the mirror M1. And this is only the rearrangement of this relation. So if you now equate this whole term to a new term, which is omega 0, and there is, so you combined all the losses to a single term, e to power minus 2 alpha RL. Now, if this means this e to power minus 2 alpha LR, it is nothing but equal to R1 into R2 e to power minus 2 alpha CL, right? Now you just have to take the logarithm in both sides. So from that you can easily see what is the relation between the total loss coefficient for unit length of a resonator with uh, the resonator loss because of the reflectivity as well as because of the propagation loss. So here you can easily see alpha R is nothing but alpha C plus alpha M. So remember the contribution of each term. Alpha C is the propagation loss coefficient and alpha R, alpha M is the loss due to the finite reflectivity of the mirror. And you can write alpha M is 1 by 2L, 1 by 2L Ln 1 by, sorry, 1 by 2L Ln 1 by R1 and R2. So please remember this equation also, because the question may be, there will be question which depend on the this equation. So this is all about the resonator loss coefficient and about the cavity lag time, which is TC. So it actually signify what is the, how is the energy, how energy is sustaining inside the resonator. So for the energy expression, you can write it as omega t equal to omega 0 e to power minus t by Tc. So here Tc is the lifetime of the cavity, that is, so if you define, if you want to find out what is Tc, Tc is the time at which the energy becomes 1 by E of its initial value. So it's the normal, I think during the first lecture, we have also talked about the lifetime. So this is also related to that lifetime, that is the time at which the energy becomes 1 by E of its initial value. So if you after a one round trip, what will be the energy? Energy will be omega 0 e to power minus t by tc. So t you can write it as, so after one round trip, it will cover a distance to L. So if it is L, so the light will propagate here, then it will come back here. So this is one round trip. So that means the total length that the light cover is 2L, and for time we have to divide it by the velocity of the ray that is propagating inside the resonator. So it will be nu. So you can write it as omega after, sorry, oh, not omega, W, that is the energy after one round trip, will be omega 0 e to power minus 2L by nu, 2L by V divided by Tc. Okay. And you already know that after one round trip, it will suffer a net loss due to the propagation loss, as well as due to the finite reflectivity of the two resonator. So that means omega 1, you can write it as omega 0 e to power minus 2 alpha R L. So if you now equate this 2 alpha RL with the term that we've seen here, so that means 2 alpha RL will be 2L by V, and V, I think you all must be knowing the relation. That is the refractive index, you can write it as C by V. So that means the velocity will be C by L. So from that, you can easily find out what is Tc, that is the lifetime, which is nothing equal to 1 by C by N alpha R. Okay. So this is how the cavity lifetime is related to the resonator loss coefficient. So if you see the diagram here, so there are different types of cavity which is different value of alpha R, that is resonator loss coefficient. So the lower the resonator loss, the more the graph will be more spread out here. So this cavity has less loss then is comparison to this cavity. If you compare these two cavities, the losses in this cavities, this graph, it is low. It is much lower than the losses in this cavity. And if you compare this to the first graph, the loss here is much more. That's why the energy it is decreasing rapidly inside the cavity. So the higher the slope, the more the losses in the cavity. Okay. So this is the cavity lifetime. That is TC is 1 by C divided by N alpha R. And for fineness, we have already seen one relation of fineness with the reflectivity. That is F is pi root R divided by 1 minus R. So now, as you know, if you see here, so omega 1, it is nothing but after one round trip, it is omega 0 e to power minus 2 alpha RL, of alpha RL. So this means after one round trip, the energy will be become omega 0 e to power minus 2 alpha RL. So you can equate it to the, you can take this term as a R square, that is it is related to the reflectivity of the mirror. And from this, you can easily value what is the square root of R. Square root of R will be e to power minus alpha RL divided by 2. From this equation, you can rewrite the fineness formula that we have seen before. That is F equal to pi root R divided by 1 minus R. So just put the formula, the relation here. And now we'll see if, let's say, we have a cavity which is a round trip loss which lies between 0.9 to 0.99. So reflection loss, it lies between 0.9 to 0.99. So for this case, we'll see if you calculate, so R square, it is related to alpha RL is minus e to the minus 2 alpha RL. So if you have values R square lies between 0.9 to 0.99, now from this equation you can easily calculate what is the alpha RL. So if you calculate alpha RL, it will be much less than 1. Like for 0.98, it is 0.02. For this case, what you can do, you can make a approximation, that is e to power minus alpha RL. So whenever this condition is satisfied, that is alpha RL is much less than 1. So you can write e to power minus x as 1 minus x. So x is alpha RL and 1 minus x you can write as x. So 1 minus e to power minus alpha RL, you can write it as alpha RL. From this, you can easily get this relation. And if you rewrite the fineness, what you will get? You will get fineness as pi by alpha R. So if you know what is the resonator length and what is the total loss inside the resonator, then you can easily find out what is the fineness of the system. If reflectivity is not given, but there is the resonator loss and length is given, then you can easily find out what is the fineness. From that, you can easily find out other parameters. Now for the quality factor. So quality factor, it is similar to the like fineness. So the more the fineness, the more sharp will be the peak is. I think you must be knowing this relation. So similarly, quality factor, it is also related to the fineness or the how sharp the peak is. So the more sharper the peak, the higher the value of the quality factor. And the definition of quality factor is this, is minus of 2 pi mu 0 energy is stored in the resonator divided by rate of change of energy. So energy stored in the resonator is Wt and the rate of change of energy is dWt by dt. And omega t relation we have seen, it is nothing but omega 0 e to power minus t by tc. So this relation is you can relate and you can easily find out what is the relation. And from that, if you put it here, then you can easily see what is the relation, what is the formula for the quality factor. The quality factor is 2 pi nu 0 Tc. Tc is the lifetime and nu 0 is the resonance frequency. And for high fineness, so delta nu we have already seen delta nu is nu f by f. So if you so nu f is nothing but free spectral range. So this is equal to C by 2nL. So and f is for high fineness it is pi by alpha or L. So this relation you have to remember it. So from that, if you put it here, then you can easily find out what is delta nu. So delta nu is that is the line width of the resonance. It is 1 by 2 pi Tc. And here we can also relate how the cavity lifetime it is related to the line width of the resonance. So this is given by 1 by 2 pi delta nu. From that, you can then calculate what is the quality factor. So 2 pi nu 0, 1 by 2 pi delta nu. So this is the value of Tc. And from this, the quality factor is nothing but nu 0 divided by delta nu. So this relation we have already seen before also. So quality factor, it is the resonance frequency divided by the line width of the resonance frequency. That is nu 0 divided by nu 2 minus nu. So this is to say it is nu 1, this is nu 2. So quality factor is nu 0 divided by nu 2 minus nu 1. So as I said, the higher the quality factor, the sharper or the narrower the resonance. So higher quality factor means the losses in the medium is much less. So by comparing the quality factor or fineness or cavity lifetime or any other parameter, you can easily find out what is the losses that is present in the what is the how lossy the cavity is and how sharp the peak will be. So this is all about the plane mirror resonator and the resonance frequency in a plane mirror resonator. So when we have two plane mirrors that is separated by a distance L, then we can see a standing mode relation. From that, you can easily find out what is the resonance frequency by equating the round trip phase equal to integral multiple of 2 pi. And from that, you can easily find out what is the free spectral range, what is the value of the resonance frequency, what is fineness, what is quality factor. So this is all about the plane mirror resonator. So now we'll see spherical mirror resonator. So before that, let us solve some few problems. These are some simple and easy problems. So please go through the question once before I solve it. So you can ask all, whether you have any doubt in the plane mirror resonator part. So please feel free to ask me any doubt. Not a lecture section, it's a live section where you can easily interact with the TA to ask your doubt, to solve your doubt, to release the concept. So please free to ask me any any doubt regarding assignment or the course, anything. Okay, so let us solve the first problem. So the first problem is so it is about consider a cavity consisting of two plane mirrors separated by a distance 31 centimeter in A. Then calculate the mode number corresponding to the wavelength lambda equal to 1550 nanometer. So it is asking about the mode number, that is the value of Q, right? So if you whenever you have this kind of problem, it's better to draw the schematic diagram, then you can easily find out what is the answer. So it is saying the lambda, it is confined between this plane mirror resonator. And whenever this lambda is confined, what is the mode number corresponding to this wavelength lambda equal to 1550 nanometer. So if you see, So standing mode in a plane mirror resonator, it is given by this type of ray diagram, right? So Q is integer. So for lambda equal to 1550, let's say the mode number is Q. So that means Q into this distance, it is how much? It is lambda by 2, right? So Q lambda by 2 equal to, so if you multiply the mode number with lambda by 2, we'll get back what is the length, what is the separation between the plane mirror resonator. So this is equal to L. So that means Q is 2L divided by lambda. So 2 into 31 centimeter and lambda is 1550 nanometer. So that means this value will go out, we will get around 4 into 10 to the power 5. So here you can see you don't have to remember the formula of the resonance frequency. You just have to uh, see what is the fundamental relation between the wavelength as well as the length L. So if you have mode number Q, then if you multiply the mode number with lambda by 2, we'll get back the what is the separation between the resonator. From this, you can easily find out what is the mode number. So mode number is 4 into 10 to the power 5. Option D. And the next problem is, what is the frequency corresponding to the fundamental longitudinal mode of the cavity in the above question? So it is asking about the mode number, the frequency corresponding to the fundamental mode. So for fundamental mode, Q is 1, right? And what is the diagram? What is the how the light is confined in the fundamental mode? So it is like this. So there is only one lobe of wave here. So that means here the L, the L, that is the distance between these two resonator, will be lambda by 2. And the lambda for the fundamental mode, it will be 2 times L. So that means L is given 31 centimeter. So 2 times 31, it will be 62. And for frequency, it is nothing but frequency of fundamental mode is equal to C by lambda. So 3 into 10 to the power 8 meter per second, and is 62 into 10 to the minus 2. So if you solve it, you can easily find this is 4.8 into 10 to the 5 Hertz. So this is the fundamental mode, the frequency of the fundamental mode. And the next question, please go through the question once. It is related to the fineness of the resonator. So it is given that the round trip cavity loss is 1%, then calculate the fineness of the resonator. So round trip loss is given, which is nothing but 1%. Then what is the value of R square? So R square will be 1 minus the round trip loss, which is 1%, 0.01. So that means this value is 0.99, right? And this value is much, it lies between 0.9 to 0.99. So that means you can easily use this formula, that is F equal to pi alpha RL. And how you can find out alpha RL? So if you recall, R square, it is equal to e to power minus 2 alpha RL. We've seen this before. If you go through the cavity lifetime once, this here. So R square is C to R minus 2 alpha RL. So that means the if you want to find out what is R square is given, it is 0.99 and it is equal to minus 2 alpha R. So that means if you take the ln both side, minus 2 alpha RL is ln 0.99. So alpha RL you can easily find out from here. It's nothing but minus of ln 0.99 divided by 2. And if you calculate it, I think we'll get around this value. It is 0.005. And for fineness F, it is nothing but pi divided by alpha RL. So we'll get pi divided by 0.005. So the final answer we'll get is around 628. Okay. Now instead of this, if you use the formula that is before approximation, I think for that case also will get in the same range. So what I mean to say, so you have one formula that is F equal to pi root over of R divided by 1 minus R. This is before approximation. So R square is already given, it is 0.99. So if you use this formula also, you can easily find out, or you can see this F also lies the same range. It is around 600 range. So in this problem, when you are using this, uh, make sure that you are using the value of R, not R square. Okay. So if you take R square instead of R, then you will get different value. So from this, if you find out what is the value of R, it will be square root of 0.99. So if you calculate it, you will get around, it's almost around 0.995. Okay. And from this, you have to take the square root of R, 0.995 square. So if you take the square root of this 995, then you will get around 0.9975. Okay. Now if you put it F equal to pi root R divided by 1 minus R. So 1 minus R is 0.995. So if you calculate it, I think you will get around 0.9975 divided by, so we'll get around 626. So you don't need to worry about whether to use this formula or that. Like the range will be same. It's like it's coming around 626. Here we'll get a higher value of F. For exact answer, if there is a range given, then you can use this. If there is no range, then use the approximated formula. Okay. But make sure you are taking root over of R, 1 minus R properly. Don't put the value of R square in this equation. So this is about the fineness of the cavity. Now let us move to the next problem. So the next problem is laser resonator has a round trip loss of 2%. Calculate the cavity loss coefficient if the length of the resonator is 50 centimeter, and what is the cavity lifetime of the given laser resonator. Okay. So one thing you have to calculate first is the cavity loss coefficient, which is alpha RL. So if you see here, so round trip loss is given there. That means we can easily calculate what is the value of R square. So R square will be 1 minus 0.02, it means 0.9. Here it is lying between 0.9 to 0.99. So you can use the approximate formula. So if you take that, that means r square is e to power minus 2 alpha rl. So from this, you can see the loss coefficient, that is the total loss coefficient, it is related to the reflectivity. So that means using this relation, you can easily find out what is the total loss in a medium, total loss coefficient in a medium. So you just have to take the ln r square equal to minus of 2 alpha rl. From this, alpha rl is minus 1 by 2l ln r square. So that means 1 by 2l ln 0.9. And L is already given, it is 50 centimeter, right? So L is 50 centimeter. So if you put it alpha RL 1 by 2 into, so it is 0.5, I think, minus 2, 0.5 and length 0.9. So this value, I think, will get around 0.0202 meter inverse. That is this much amount of loss per meter in the cavity. Now you have alpha RL, alpha R, that is the total loss in a cavity. So we have seen before the alpha RL, it is related to the cavity lifetime as well as it is related to delta nu. So if you already calculate the alpha R, then we can now calculate what is the cavity lifetime. So TC we have seen before, it is nothing but 1 divided by C by N alpha R, right? And N we are taking is, if no medium is given, take N as 1. So 1 by C alpha R. So C value you already know, this is 3 into 10 to the 8 meter per second and it is 0.020. Okay. And from this, if you calculate it, I think you will get around 16.5 nanosecond. Okay. So this is how you can calculate what is the loss coefficient in a medium and the cavity lifetime. Now we'll go through one final problem, then we'll move on to the spherical resonator part. So up to now, are the problems, the solutions are clear to you? I think the solutions are okay for you. Then let us move to the next problem. So the last one is a laser resonator has a round trip loss of 5%. Calculate the quality factor if the resonator length is 1 meter and the wavelength of the laser is 500 nanometers. So what is given to you? The resonator length is given, which is 1 meter, and the wavelength that is confined, it is 500 nanometer. And there is a loss of round trip loss of 5%. So that means R square will be 95%. So it is 0.95. So calculate the quality factor. So if you recall, quality factor is nothing equal to 2 pi mu 0 Tc, right? So this you can rewrite as 2 pi mu 0 Tc is C alpha R, and mu 0 you already know it is C by lambda 0. So that means C will cancel. So you will have 2 pi lambda 0 alpha R. So depending on the parameter that is given to you, you have to rewrite this equation. So length is given. So that means if you multiply L here, and divide L here, then you can see now the quality factor expression will be 2 pi, sorry. So fineness, you already know fineness is pi by alpha R. So that means you can rewrite this pi by alpha RL as fineness. So quality factor will be 2LF divided by lambda 0. And these all are given. F you can calculate it because R square is given is 0.95, and from this is minus 2 alpha RL, right? Is 0.95. So you can easily find out what is alpha RL here by taking the ln in both sides. It will be minus of 0.95 divided by 2. And the value will be, so if you calculate fineness using this value, then fineness will be pi divided by alpha RL, and you will get around 122 fineness. And fineness is already given, lambda is already given. So 2 into 1 meter, L is 1 meter, F is 122, and lambda is 500 nanometer. So 10 to minus 9. Okay. So using this, if you calculate it, you'll get the quality factor is 1.5 into 10 to 9. So you have to relate all this equation and relation to find out the value for the other parameter. So I have solved 5 problems. Yes,
Gitanjali ma'am, uh,
yes.
I R square is equal to P to the power minus 2 alpha RL is uh, right for every R, not for high fineness.
R square is equal to e to power minus 2 alpha RL. It is valid for all R.
All R.
So,
But in case
हाँ,
of high fineness, uh, we can use alpha RL here is if we have high fineness, then we have R square equal to if 0.9, then in that case, if high fineness RL is 1 minus 0.9, I think.
I didn't get it. Can you please repeat? So round trip loss is 5%. Then
High fineness slide. We showed the high fineness slide.
high fineness light. This one.
And here you can see that our R square equal to 0.98, uh, alpha RL equal to 0.02, and which is 1 minus R square, I think.
Uh, alpha RL is 0.02.
It
Uh,
is 1 minus.
whenever okay, so the after taking the ln and divided by so after taking the ln, you are getting the same value, right? So you are telling even if don't take the ln, then we'll get alpha RL is 1 minus R square. So if let us move to our problem. So here it is 0.02.
So, ma'am, in this case, this value will just 0.01.
Um, I doubt because if you see this problem, here
Yeah,
the cavity loss is 1%, right?
that's why that That's
But
why I'm asking, I asking the
uh,
previous interaction lecture due to this slide.
oh, due to this slide.
Yeah, yeah. Because if we consider this, then the difference between normal formula and this formula will much there.
So let us calculate whether alpha RL is 0.02 or not here. So R square is given is 0.98. So yes, it will be by 2. So if you calculate it, it is approximately equal to 0.01, not 0.02. Um, okay. Okay, so let's verify it. Okay, so let us verify this slide, whether the solutions are coming different or not. So we'll calculate using two formula. One is, let's take the first formula, which is pi equal to, sorry, f equal to pi root over r divided by 1 minus r. So r square is given, it is 0.98. So using this, let's calculate what is f. So if it is, then r we can calculate it is will be square root of 0.98, which will come around 0.98995. And if you put it, so it will be pi root over of 0.98995 divided by 1 minus 0.98. So what is r? 3.14 into square root 0.98 and then 5, 1 minus 0.98995. So from using this, it is coming around 310. So let us see whether we are getting the same fineness using this formula. So r square is again 0.98. So I think I will suggest don't take alpha RLS 1 minus r square. So you already know r square is, so calculate from this formula.
Okay.
So here you can find
That
out
is
alpha RL is, it will be minus of ln r square divided by 2. So r square is 0.98. So let us see ln ln 0.98 divided by 2. So it is coming around 0.01. If you take the maximum as this, then f is pi by 0.0. So it will come now 3. It is already 3.14. It is 0.01. It's already 314. So don't take. Okay. So there is a mistake here. I think instead of 2, it will be 1.
okay. Okay.
Hmm. If you take 2, I think there will be error. because it will be 314 divided by 2. So that's why we'll get different. So don't take 1 minus r square as alpha RL. So use ln formula to calculate.
Okay.
Okay. And any other doubt in the slides or in the problems? Anyone? Otherwise, we'll move to the content of week 6. So I think the problems as well as the slides are clear to you. If you have any doubt, you can write it in the chat box, or you can unmute yourself to ask your question. So now let us move to the next problem. Sorry, next week 6 content. So next one is in week 6, we saw what is spherical mirror resonator, what are the modes in the spherical mirror resonator, and what is the ray transfer matrix. So why do we use spherical mirror resonator? So in the plane mirror resonator, we have seen only certain parts, certain ray paths are allowed. So if you see if the plane mirror, if there are two mirrors, plane mirror that is separated by distance L. So only the ray that is normal to the mirror surface, they are confined. So whenever the ray makes an angle with the mirror, they will eventually escape out the resonator volume. So if you have let's say we have a ray like this, which is making an angle to the mirror surface, then after few reflection, it will eventually escape out the resonator volume. So that means there will be diffraction loss in the plane mirror resonator, which we won't see in the spherical mirror resonator. So that's why we use spherical mirror resonator to compensate the diffraction loss, which is suffered in the plane mirror resonator. So if you see the spherical mirror similar to the plane mirror, we have two spherical mirror, M1 and M2, that are separated by a distance L. And this M1, M2 has the radius of curvature R1 and R2. And in this spherical mirror, whenever there is a diverging beam, let's say the ray is going like this. So because of the focusing effect of the next mirror, because of the focusing effect, it will be reflected by this mirror, and it will be focused back. So that is why we can minimize the diffraction divergence by using a spherical mirror resonator, and we'll see very low propagation loss if you use a spherical mirror resonator. And similar to the longitudinal mode, we can also define the modes of the resonator as a transverse mode by looking at the electric field profile. So how the electric field is varying along the transverse direction. Okay. Longitudinal means along the length of the resonator. Transverse means perpendicular to the length of the resonator. So transverse mode, as I said, it is refers to the transverse field distribution of the propagating beam in the resonator. So in a plane mirror resonator, we don't have any analytical expression because of the diffraction losses. We'll see we don't have any analytical expression, and if you want to find out what is the expression, then we have to do it numerically. Okay, and if you see a spherical mirror resonator, we'll see that the transverse mode, you can write it as either Hermite-Gauss field distribution or Laguerre-Gauss field distribution. So it's the field distribution, that is the transverse mode, it's a multiplication of two functions. One is Gaussian field and another one is the Hermite polynomial. And we have a Gaussian field multiplied by Laguerre polynomial. And the Gaussian mode in the system is the fundamental mode of the system. If you see the fundamental mode, so the mode it resembles the Gaussian field distribution. Okay, And for the Gaussian mode, let's say we have two mirrors, two spherical mirrors. A mirror one, which is R1 is 1. R1 is 1 means 100% reflection, and R2 is 0.9. That means 90% reflection and 10% transmission. So in this system, what will happen whenever the light is confined, it is moving back and forth between these two mirrors. Some of the modes that is confined, the transmodes mode correspond to that mode that which field distribution doesn't change over time. That is, the field is confined within this. The distribution is same inside this resonator. And if you see the fundamental mode, so fundamental mode it varies. It behaves like a Gaussian field distribution, which is expression. If you see, psi is a e to power minus r square by w square. So, uh, if you look at this figure, so these are two surfaces. So the Gaussian beam, it is starting from here, that is z equal to 0, and it is slowly moving towards the second mirror. So now we'll see. So as the ray propagate, it will broaden inside this uh, resonator volume because of some losses in the system. So because of the losses, we'll see the narrower beam gradually become broader, but the energy content, it will remain same throughout the volume. Okay. And W is nothing but the wave size, and R is the radius of curvature of the wavefront. And some common types of resonator. If you, I think one of the lecture we've seen concentric and confocal resonator. Here we for the spherical mirror resonator, we can also see these two types. That is symmetric confocal resonator. So confocal, as the name indicate, it is the mirrors have same value of same value of focal length. So that means if you have two mirrors, let's say mirror M1 and mirror M2 that are separated by a distance L. So the center point will be the distance at which the distance between the distance of the mirror from the center point will be equal in either side, right? That is, this distance is equal to this distance. So that means this center point is nothing but the focal point of this setup. So in this case, you can write L as F1 plus F2, and F1 is nothing but R by 2, and F2 is also R by 2. And you can also tell this F. So F1 and F2 are same, so that means this is 2F, and F is nothing but R by 2. So that means L is R. So L is the distance between this mirror is nothing but the radius of curvature of one of these symmetric resonator. So in this resonator, if let's say we have a ray path that is going parallel to the resonator volume. So whenever the ray it travels in a straight manner, it will be directed towards the focal length. So after reflection at the mirror 2, it will passes through this focal length. So whenever now the when the ray passes through the focal length, so it will now suffer a reflection from the mirror M1. So the reflection will be now become parallel to the resonator volume. So whenever it is traveling in a straight manner or parallel to the in a straight line path, so it will go through the focal length. And then after going through the focal length, it will be reflected back at the mirror M1, and it will again goes straight in a straight manner. And from the surface, it will again be directed towards the focal length. Now it will be a complete round trip. So now the ray will uh, again follow the same path after this round. So here you see after two round trip. So after two round trip, this ray retraces the path. So round trip here it indicates how many number of times it is coming to the same mirror. So if you see it is going through this mirror, then it comes here. So first round trip, then it again go through this mirror, then it again get reflected to the first mirror. So second round trip. So after two round trip, it will again follow the same path. So that is why we'll tell the in this symmetric confocal mirror resonator, after two round trip, the ray will retrace the path. And there are some sign convention that we'll use to solve the ray transfer matrix. That is the value of R, the radius of curvature for the concave mirror. It is less than zero, and for the convex mirror, it is greater than zero. So these are some sign convention. There are some more sign convention. We'll see in the next few slides. So this was all about the symmetric confocal mirror resonator. The next is symmetric concentric resonator. So concentric, as the name indicate, it is same values of same value of radius of curvature. So instead of focus, we have same value of radius of curvature. So that means this now the center, the distance between the first mirror to the center point, it will be R instead of F. Okay. And if you write down what is the length, so L will be is R plus R, that is 2R. So L you can write is mod of 2. So we are taking 2 mod of R because for concave mirror this R is negative, but length is a positive parameter, so that's why we are taking 2 mod of R. And in this concentric mirror resonator, we'll see if it is R, that is when the ray, when it passes through the center point. So you can easily see this will be normal to the surface of this mirror. So whenever the ray incident in a normal mirror, it will be reflected back. So that's why after each round trip, we'll see there is a and the ray will retrace the path. Okay, for the concentric mirror result. And another type of arrangement that we can have, it is plano concave mirror. So one is instead of two spherical mirror, we have one plane mirror and one concave mirror. So M1 is the plane mirror and M2 is the concave mirror, and the distance between distance between them is F. In this mirror, if now the ray is traveling like this, that is parallel to the resonator volume, or parallel to the parallel to the axis of this resonator, then it will be directed towards the second lens. Now it will get reflected to this lens and it will move parallel to this surface. So here you can see after 4 round trip, that is after 4 round trip, the ray will retrace the path. Okay. So these are some kind of resonator. So now you can also divide the resonator as either stable resonator or unstable resonator. So stable means the energy it is confined inside the resonator volume. Unstable means it will leak after some time. So the example of unstable resonator, it is one is the plano convex mirror. So when you have one plane mirror and one convex mirror, instead of concave, we have convex mirror. So in this case, because of the diverging effect of this convex lens, so you know that the convex lens is diverging. So whenever the ray incident on this convex mirror, it will diverge out. So instead of confining the mirror, it will diverge out. So that's why the ray will eventually escape the resonator volume. So that's why the plano convex mirror, it is a unstable resonator. And another type of resonator is the setup where we have two convex mirror. That is mirror M1 and M2, both are convex. So here we'll see no matter how the ray is covering, it will diverge at the second mirror. So that's why the light will not be confined inside this resonator volume. Okay. So these are two examples of unstable resonator. And another type of, if you take one convex and one concave. So if you see, if you make some parameterization, like take some specific value of F and R, then you can make a stable resonator for one convex and one concave mirror. Okay, let's see in the next few slide. Now we'll see the ray paths, how the ray is it is traveling inside the resonator volume, or it is varying inside the resonator volume. So for this, we'll use the matrix optics, uh, which is mostly used under paraxial approximation. So paraxial means it is parallel to the axis. It is almost parallel to the axis of the resonator. Okay. So whenever the almost parallel means it makes smaller angle to the axis of the resonator. So axis means this point, the central line that passes through the center and it divides the resonator into two parts. So this is the axis. So now whenever the ray, let's say take this ray, whenever the theta angle, it makes small angle to this resonator, then we'll see we can make a approximation, paraxial approximation, that is tan theta and sine theta you can approximate as theta. Okay. And these are also valid in practical laser. If you see the practical laser, that is the helium neon laser that you use in, I think, single slit experiment, you use helium neon laser. So for that case, if you see the divergence, that is the ray that is traveling, that is traveling outside this resonator volume, it is theta of 1 milliradian. So that means you can make the paraxial approximation here. So this is not like it is not valid practically. So you can use it in the practical system. So for this system, we'll see how the ray, what is the ray transfer matrix, how the different parameter can be approximated using this matrix optics. So ray transfer matrix. So it is like how the input is related to the output beam. So this is the ray transfer matrix. So let us see. So let us, if you see this diagram, the figure one, it is the red box. It's the optical system. So the optical system will have different optical element. Can have different type of mirror. Can have a beam splitter. Any optical setup, optical element will be inside this optical system. And what we see in the rate transfer matrix will relate what is the input and how the input is related to the output rate. Okay. So if we take two parameter for the input, that is yi and theta I. Yi means what is the so at the point of incidence. So when so for the ray one, it is incidentating at the point, this point here. So what is the distance between the point of incident to the central axis? So this I. So this is yi, and theta is the angle that the ray makes with the axis. Okay, horizontal axis. And for the ray 2, we'll have y0, which is the height of this ray that is emerging out of this optical system with the central axis. And theta is the angle that the ray make with the horizontal axis. And we'll see that this y theta, so y0 and theta 0, this is related to this yi theta I through this ray transfer matrix, which is ABCD. So ABCD are the matrix element. Let's see what is the ABCD for different type of setup. And as I said, the optical system, which is the black box here. So here we can have different mirrors like Can be a plano convex lens or two plane mirror or two symmetric spherical mirror. It can be anything. So it can have any number of mirror or any number of optical elements here. And whenever the ray comes here and goes like this, we'll relate what is the yi theta I through this ray transfer matrix A, B, C, D. Okay. So as I said, ray transfer matrix, it's a 2 cross 2 matrix that relates the input and output parameter for a ray through an optical system. So now let us see how you can we can find out what is ABCD. So for that we have to see how the ray is how is the ray path during the propagation of light or during the uh, oscillation of light between this two mirror resonator. So for spherical mirror, we'll see for the spherical mirror resonator first. For spherical mirror, if you start from here, so we'll see it propagate like this. So there will be a matrix that is related to this propagation length. Now it get reflected here. So there we will define a matrix for this also, reflection. Now the reflected ray will propagate towards the mirror M1. So for this propagation, we'll define a matrix. After this point, it will again reflected from the mirror surface M1. So for this also, we'll define a matrix for this reflection at mirror M1. So we'll see after one round trip, we'll see the light propagate through the length, that is this path, then get reflected, then again propagate through the length, then get reflected from here, right? So now this propagation, reflection, you can define the whole behavior as A, B, C, D. So let us see one by one. So first one is the propagation rate. So when the ray propagate, how the yi theta I, how it evolves during the propagation of ray during in this mirror resonator. So if you see the first one, it's a plane mirror resonator. If you see this, so this is y in and theta in. So the ray is starting from here, right? So it is now propagating inside the medium before reflection. So y in is the height of the ray from the central axis, and theta is the angle that the ray makes with the horizontal line. And after before reflection, the height will be y out and the angle will be theta out. Now, here you can see the ray is propagating inside the medium before reflection. So when the ray, if you consider a homogeneous medium, so in homogeneous medium, the ray travels in a straight line. So it doesn't bend in a homogeneous medium. So for this case, you can, if you see it travel in a straight line, that means the angle that the ray make with the horizontal axis, that is, if it is moving in a straight line, that means these angles are same, right? It is not going any other deviation. So that means these angles are same. So that this means theta out, it will be equal to theta in. And for y out, what we can do, so out, it is nothing but y in, which is this part plus this additional part. And this additional part you can uh, find out using the per excel approximation. So this is the additional part where we have angle theta in, and this is the length L, right? And we know that tan theta, it is nothing but this additional distance, let's say P divided by L. So that means P equal to L tan theta in. And for paraxial approximation, you can use tan theta in as theta in. Okay. So that means Y out. It will be equal to L theta in plus Y in. Now, to express this behavior, how the Y in and theta in are changing, we use matrix. So now we'll express this y out and theta out in terms of y in and theta in. So y out, you can easily see it is L theta in. So let's say this y in plus L, sorry, 10 not 10 theta in. And out is theta out is theta in. So if you want to express in terms of y in and theta in, so this theta out you can write it as 0 times y in plus 1 times theta in. So that means, okay, so let me write out clearly. So this is nothing but y out is y in plus L times theta in. And theta out is nothing but 0 times y in plus 1 times theta in. So that means the matrix element is, here it is 1, it is L 0 1. So that means y out theta out, if you write it in terms of matrix, so it will be 1 L 0 1 y in theta in. So this is the matrix that express, that shows how that shows the propagation behavior of light inside the resonator. So if you want to find out what is the propagation behavior of a ray, then you have to use this matrix 1 L 0 1. And the next part is, okay, before going to the next part, let us see the sign convention. So sign convention, you know that I have already told one sign convention, that is the radius of curvature. For concave mirror, the radius of curvature it is less than 0, and for convex mirror, it is greater than 0. And for y in and theta in, what we take, that is, if y is above this central line, it is positive, and if y is below this central line, then it is negative. Okay. And similarly, theta is, if it is making positive angle, that is like this, then theta is positive. And if it is making negative angle, then theta is negative. So these are the sign convention that you must remember to calculate the ray transfer matrix. Okay. And the next part is after propagation. So you've seen after propagation, it will be reflected back at this mirror surface. So now we'll see what is the matrix for this reflection. So reflection, if you are considering reflection, then reflection is occurring at a point, right? At a point at the mirror surface M2. So that means both the incident ray and the reflected ray, the y in and y out for these cases are same because they are occurring at a point. So that's why we'll take y in is equal to y out. Okay. And theta in is always equal to theta out because this is the angle of reflection. So whenever it makes an angle theta in with the sen- with the normal, then the angle of reflection will be equal to the angle of incidence. So that means the theta in it will be equal to theta out. So for this, you can see it is nothing but the matrix is 1001, right? 1001 y in theta in. So this is for the reflection. And for the next part, let's say there is in addition to reflection, we have a refraction here. So light will get refracted to the second medium. So for this case, what we have. So similarly, refraction also occur at one point here. So that means y in is always equal to y out. And for the angle, you can use what is Snell's law. So you already know what is Snell's law. That is n1 uh, sine theta in equal to n2 sine theta out. Okay. So if you use it, then 1 minute. Uh, then you have to use the paraxial ray approximation. Okay. So paraxial ray approximation is sin theta is always approximate equal to theta, or tan theta is approximately equal to theta. So that means theta in and theta out, these are related by n2 by n1, and there is no relation of theta in with y out. So that means it this refraction. So in reflection we have seen 1001, but in refraction instead of 1 here we'll see n1 by n2 because of the refraction. So whenever let's say you are given two medium of different diffractive index, then you can easily find out what is the ray transfer matrix for that case if you put the refractive index of these two mediums. So make sure you are putting the right order, that is n1 by n2 instead of n2 by n1. So this is all about, I think these alls are about the plane mirror. So now let us see the reflection at a spherical mirror resonator. Okay. Up to this, is everything clear? So we have seen the reflection, refraction, and the propagation in a plane mirror resonator. Now we'll see the spherical part. So for the spherical part, what we have, so let's say the rays propagating, making an angle theta in with the central axis. Okay. So that means, and reflection is, we have seen, it occurs at a single point. That means y in is always equal to y out. And there is a relation between theta in and theta out. So if you see this image, so the ray will hit the mirror surface M2 and it will be reflected towards the mirror M1. So for this case, if you join the center of curvature to the point of incidence, so that means this line will be normal to the mirror surface M2, right? So that means this angle, it will be equal to this angle. So angle of incidence is equal to angle of refraction. So this will be theta and theta. And if you want to find out theta in, so if you see, this is, let's say that this is theta C and this is theta out. Okay, one is theta C, that is the angle that the center point, the line joining the center point makes with the central axis. And one is theta out, that is the ray, the reflected ray makes with the central axis. So, so from this you can easily find out. I think these are easy to find out. So theta in, so theta C is equal to this angle plus this angle. So that means theta in is theta C minus theta, and theta out, it is theta C plus theta. So theta out means theta C plus theta. Now if we sum it, theta out and theta in, we'll get 2 theta C. And for you already know that for paraxial, you can use this. Tan theta is approximately theta, or theta is approximate equal to tan theta. So in the next part, we have already, you have just use this paraxial approximation so that you can relate y out and y in. Not sorry, you can find out the relation between theta out with y in. Okay, so tan theta c, if you take this triangle, so here tan theta c, in this triangle it is nothing but y out by divided by r, right? Or minus of 2y in by r. So we have taken minus because this is the concave mirror, so r is negative. So if you put it here, the equation, that is the relation we will get is this. And if you rearrange it, The final ray transfer matrix for a reflection at a spherical mirror, you will get 1, 0, 2 by R, 1. So this is the ray transfer matrix for the reflection of the spherical mirror result. Now we'll combine all, that is propagation, two propagation and two reflection of the ray. So propagation you have already seen, it is denoted by 1L01. Then there is a reflection at the spherical mirror. So it will propagate. So the transfer matrix is this. Now it will get reflected. For this, the transfer matrix is this. We've seen now only 1, 0, 2 by R2, 1. Now the ray will again propagate. For this, the transfer matrix is 1L01. And for this, it will get reflected again. And for this reflection, the transfer matrix is 1, 0, 2 by R1 and 1. And the product of this four matrix, it is what they call ray transfer matrix, A, B, C, D. Okay. I think everyone must be knowing how to do the multiplication in a matrix. So if not, you can ask. I will show the step how to calculate the multiplication. So I'm assuming you know how to multiply the matrix one by one. So if you multiply it, what you will see that these all four matrices after multiplication will get A, B, C, and D. So these are the terms that we'll get after the multiplication factor, and these are the parameter we'll get. Now, for each setup, like let's say we have plano-convex lens, plano-concave lens, or two convex concave lens, then you can put what is the value of R1 and R2 to simplify this ABCD value. Okay, and this is all about the ray transfer matrix. So these are some additional relation, that is we have already seen after one reflection, the matrix, that is y1 theta 1, it is related to y0 theta 0 is AB is y0 theta 0. Now after second round trip, so second round trip what we'll have, will have y2 theta 2 is ABCD y1 theta 1. So instead of y0 theta 0, it will be y1 theta. So that means after m round trips, we'll have the matrix relation as ym theta m equal to abcd to the power m y0 theta 0. Okay. So these are all about the ray transfer matrix. So now let us move to the stability condition of this mirror. Okay. So after solving this, we will solve a few problems also, so that it will help out to understand the concept. So this we have already seen. So this is the ray transfer matrix for the spherical mirror resonator. The exact expressions are this A. B. You don't need to remember all this relation. If it is required, it will be given in the problem. Okay. And if you see each matrix, the determinant of all is 1. So determinant of a matrix A, B, C, D, how you can calculate it? So determinant is, it is AD minus BC. Okay. So that means if you have, let's say, matrix 1, L, 0, 1, so determinant is 1 into 1 minus 0 into L, it is 0, so it is 1. So this is, we just have to cross multiply the terms. Is to this. So if you see it, the determinant is always 1 for each of this matrix. And when you have this situation, like let's say we have 4 matrix, instead of taking ABCD, let's take N1, N2, N3, N4, which is given by a final matrix, let's say A. not A, let's say capital A. So that means to find out the determinant, it is nothing but determinant of n is equal to determinant of n1 into determinant of n2 into determinant of n3 to determinant of n4. So that means the determinant of ABCD, the final ray transfer matrix, it is 1 only. Okay. And this we have already seen before, so I'm skipping this slide. Now, uh, these are some equations to find out the resonator stability condition. So to find out the resonator stability condition, we have to express the Ym and theta m in terms of only one parameter. Either take Ym or theta. So let's replace theta by y. So these are relation we have already seen. That is Ym plus 1, it is related to Ym theta m by the ray transfer matrix ABCD. So from this you can easily find out these two relation to multiply row by column. And from this one you can take theta m is nothing but, okay. So theta m it is calculated from here, and from this first equation, theta m, you can calculate theta m, it is Ym plus 1 minus Aym divided by B. So that means theta m plus 1, you can also write it as, just replace m by n plus 1. So that means this theta m plus 1 will be Ym plus 2 minus Aym plus 1 divided by B. Now you already got what is how theta m and theta m plus 1, it is related to Ym plus 1 and Ym plus 2. So you just have to put in equation 3 now, sorry, equation 2 to find out the final expression. Okay, I think these all are clear. So I'm skipping this all equation, these intermediate steps. In equation 5, what we have done, AD minus BC, it is nothing but determinant of ABCD matrix. So we have put 1 here, and A plus D, we have make a substitution, that is A plus D, we have taken as 2B. Let's take it is 2B, 2 times of B. Now, if you put it, the equation 5, it will become equation 6. So it is now we take a trial solution. So whenever we have this recurrence relation, then we'll take trial solution to find out the approximate uh, solution to this problem. So the first trial solution we can take is Ym. It is y0 s to power m. Okay. So if you now check for m equal to 0, for m equal to 0, it is y0 equal to y0. That is when the ray is starting, the value of y is y0. So LHS satisfies the RHS. Okay. Now what you have to do, you just have to put this expression here. So if Ym is y0 h to power m, that is Ym plus 2, is y0 h to power m plus 2, and Ym plus 1 is y0 h to power m plus 1. So you just have to put this and factor out the common term. The common term is y0 h to power m. So if you factor out it, you will get a polynomial equation, quadratic polynomial equation in terms of h. Okay. This solution you already know. So it is minus b plus or minus root over b square minus 4ac divided by 2. So if you put it, the value of h will get is this. Okay. And what we have done in the next part, we have just rearranged the term. That is, instead of writing as b square minus 1, we have to write it as 1 minus b square. So if we write it in this manner, so what we can do, we can take a substitution, that is phi equal to cos inverse b. So that you can write this term 1 minus b square is sin square phi. Okay. So if you put this, I think these are all obvious from this relation. If not, you can ask me. Okay. So I'm assuming these steps are known to you. So so B, you have put the value of B here, which is cos phi plus or minus I sin phi. And this is nothing but e to power plus or minus I phi. Okay. And that means the Ym, it is y0 e to power plus or minus Im phi. And this plus or minus Im phi, you can rearrange it and write it as a P cos m phi plus Q sin n phi plus for some values of P and Q. So these are some rearrangement we can take or we can use during solving the problem. And the final form that we'll get is y0k sin n phi plus phi 0, or y0k you can take is as y max sin m phi plus phi 0. You can see the y, that is the distance, it is varying sinusoidally. So that means it will be bound whenever the value of phi is real. So if it is real, then it will be bound inside the cavity. So phi is real means the value of cos phi, it should lie between -1 to 1. So that means B mod of B, it should be less than equal to 1, or B should lie between -1 to 1. And B, we have assumed B is to be as A plus D, that is B equal to A plus D by. So please remember this relation. So this will be useful while solving the problem. And A and D, this will be shown how you get this relation in the next slide. So for now, if you take this, that is, take this formula, take this relation, what we see, the resonator condition, it is given by this form. And we take this factor G as G1, and this second factor is G2. So G1 is nothing but 1 plus L by R1, and G2 is 1 plus L by R2. So this is the resonator stability condition. So this equation is important. So this will tell whether the resonator that you are considering is a stable resonator or unstable resonator. Now we'll see what is the upper limit and the lower limit of this equation. The upper limit is when lower limit, let's see the lower limit first. Lower limit is G1, G2 equal to 0. That means either one of this factor is 0. That is either G1 is 0 or either G2 is 0. And the upper limit is the maximum value that G1 and G2 can take is 1. So that means for that case, G2 will be 1 by G1. And if you plot this relation, we'll get a graph. This is known as the stability diagram. Okay. So this is the stability diagram. So lower limit is this scales, where for this scale it is G2 is 0, and for this scale it is G1 is 0. And the upper limit is given by this blue curve. It is 1 by G1 or 1 by G2. And the reason that is inside this upper and lower limit, that defines the stability, the reason for the stability resonator. So this shaded region, these are the stability region. Okay. So all setup that we will see, it will fall inside this stability region. So if you see in the diagram, there is a resonator, which is a value that lies in this region or in this region, let's say in this or in this. So these are unstable resonators. So all the two convex mirror, they will lie in one of this unstable region, or we have seen one plane mirror with one convex mirror. So this will lie in the unstable region, and whatever the confinement, whenever there is a confinement, we will see the G1 and G2 value, it will lie inside this stability diagram. Okay. And okay, so let's say we have two plane mirrors. That means the R1. So for plane mirror, R1 is infinity and R2 is infinity. So please remember all this simple relation. So R1, R2 infinity, that means G1 is 1 plus L by R1. So this will be 1 and G2 is 1 plus L by R2 is 1. So that means G1 and product of G1, G2 it is 1 and it is lies between 0 to 1. So that means this point here it indicate a resonator when we have two plane mirror resonator. Okay, 1 and 1. And similarly, this is about the plane mirror which lies in the 1 1 point. Now, if you see the symmetric confocal mirror, let's say we have two concave mirror. So please remember for concave mirror, R is negative. For this setup, we have already seen the length L. This equal to, if you write in terms of sign, it will be minus of R, right? So that means if you find out G1 is 1 plus L by R1, so it will be 0 and G2 will also be 0. That means the origin, it defines a setup where we have resonator which consists of two symmetric convex confocal mirror. Okay, and for concentric, if you are considering concentric mirror resonator, for this we have L equal to minus of 2R. So that means the G1, G2. To take G1 is 1 minus half, right? So it will come around, what is minus 1? So it is L is 1 plus, sorry, G1 is 1 plus L by R. Okay, so in the top, this is minus 2. So 1 by 2, sorry, 1 minus 2, it is minus 1. So G1, G2, it will be minus 1. So that means the point here, it is minus 1, it indicates a setup where we have two concentric mirror. And for all symmetric resonator, we'll see the value of G1 and G2 will lie in the straight line, this symmetric line. So for let's say we have two plane mirror, then it is 1 1, or two confocal mirror, it is at 0 0, or we have two concentric mirror, it is at -1 -1. Okay. And for symmetric mirror, the R1 and R2 value are same. That means you can take G1 and G2 as G. And if you take it, that means the G value, it should be lies between -1 to 1 for stability. And just put the value of G, which is 1 plus L by R. From this, we can easily find out what is the value of, what is the stability condition. That is, the 0 should be greater than, sorry, 0. The 2 plus L by R should lie between 0 to. So here you are already seeing it is 2 here, already is here, and it is less than 2, means this factor should be negative, right? So that means the R should be negative. If you are taking a symmetric mirror, R should be negative or R should be infinite. So that the maximum value of 2 plus L by R is 2. So it is that these two values satisfy this equation. So that means you can take a plane mirror resonator, or negative value of R means you can take a concave mirror. Okay. So for symmetric, for stability, we have two mirrors. One is plane mirror or concave mirror. And this is, please go through this. I think this is easy to find, get the relation. This shows how this stability condition is arrived. So if you see this one, this relation is, so how you get here to here. So this is written here. I think this is easy, so I'm skipping this exercise. The next is the next we'll see is the ray paths in the spherical mirror resonator in our next live section. We'll finish all this in the next session and we'll solve the problems also. Before that, let me ask whether you have any doubt up to now, whatever I have discussed. The ray parts, which is nothing but the numericals, will solve in the next section. So we have done till. And regarding the slides, let me, if you want, I will upload the week 6 slide in my Google Drive link. I will upload there. You can go to that site, go to that link to get the slide for week 6. And solution for week 4, I will tell them to release the solution. I think they have forgotten. So let me tell them to release the solution. And do you have any doubt till now? Okay. If you have no doubt, so I think the problems, I think we have solved 5 problems regarding the resonator loss coefficient or the quality factor, cavity lifetime. I think that problems as well as the concept, that is the content of this week 5 and week 6, some part of week 6, these are clear to you. And if you have any doubt, if you are not finding out now, then you can ask me in the next section. For now, let us end the section. So thank you for joining the section. I hope these problems and the concept as well as the numericals, these are all clear to you. And we'll meet on next Saturday, same time from 4 to 6. And till now, if you have any doubt, you can write it in the discussion forum or you can ask me in the next live section directly. Okay. So let us meet on next Saturday. So goodbye, everyone.
Thank you, ma'am.